All right, everyone, so this is going to be the very first experiment for the OChem lab, the purification of benzaldehyde. So you can follow along with me in your textbook, pages 75 through 76, or which can also be found on Blackboard. So just a little bit about benzaldehyde. You can see the benzene ring as well as the aldehyde, so benzaldehyde. Another name for it can also be benzene carboxaldehyde. The formula for it is C7H6O, and it has a molecular weight of about 106.12 grams per mole. Something important for this experiment is it's a colorless organic liquid at 23 degrees Celsius. And I guess something fun about the benzaldehyde is it's what gives almond that almond-like odor. And we actually can use benzaldehyde to give that odor and flavor to candies. But yeah, so it is actually the chemical that is used for that almond-like smell and taste. It has a density of about 1.44 grams per ml, a boiling point of 178 degrees, and something else kind of important to this lab is that it is not miscible in water. So what's very interesting about your very first experiment is we're not actually making a product that we're going to use. We're actually just trying to clean up our benzaldehyde so that we can use that. So the reason is benzaldehyde can undergo autooxidation. This means that our benzaldehyde can easily be oxidized by atmospheric oxygen and form a carboxylic acid. So this can be seen here, where we have two molecules of benzaldehyde and a molecule of oxygen. And what will end up happening is this oxygen will kind of come over here and form two benzoic acids. And so because of this, benzoic acid is a very common impurity in our benzaldehyde stock bottles. So I just want to kind of go over the mechanism of how autooxidation occurs with benzaldehyde. So it first begins with the homolysis of benzaldehyde and oxygen, where benzaldehyde produces a single radical, and oxygen will be a biradical or a diradical. The two can then react with each other, where the radicals will bind, so the oxygen to the carbon, oxygen to the hydrogen, to form peroxybenzoic acid. Once peroxybenzoic acid is formed, it can undergo heterolysis, where the hydrogen can be removed, leaving a negative charge on the oxygen. Another benzaldehyde molecule can come, where the oxygen can react with that proton. This causes the oxygen on benzaldehyde to have a positive charge, making this a carbocation. So our negatively charged oxygen on our peroxybenzoic acid can attack the carbocation, breaking this double bond and forming this transition state. From here, the hydrogen can come, form a double bond, can be removed to form the double bond to this oxygen and break this bond to this oxygen. So we are now left with two different compounds. The oxygen that was on our once peroxybenzoic acid is still negatively charged and can pick up this hydrogen that has been removed to form two benzoic acids. So we don't want benzoic acid in our benzaldehyde. We want to use pure benzaldehyde for the future experiments. So what we need to do is remove this benzoic acid so that all we're left with is benzaldehyde. And we can do this by using sodium carbonate. So sodium carbonate is a base that will react with benzoic acid. So here you can see that if benzoic acid undergoes heterolysis, where the hydrogen is removed, our benzoic acid, the negative charge on the oxygen, can ionically bind to the sodium, and the negatively charged on the carbonate can interact with the hydrogen. And so what we end up getting is sodium benzoate as one product and sodium bicarbonate as another product. So what's good about this is sodium benzoate is a salt that's very polar, meaning it is very, very soluble in water. And because benzaldehyde is nonpolar, it is not soluble in water. So we can kind of use this to our advantage to separate our benzaldehyde from the benzoic acid. So we're going to be using a very simple water extraction to separate benzaldehyde from sodium benzoate. So here are the steps in the lab that you'll be seeing in the other lab video posted by Dr. Salvador. So the first thing that you do is you prepare a 10% by weight sodium carbonate solution. And it says that each group needs about 10 to 15 mLs. So when you see 10% by weight, it's usually weight by volume. So that means if we're working with 10 mLs of solution final volume, we would need about 1 gram of sodium carbonate, because 1 is 10% of 10 for you guys. So let's say we want to find the amount of sodium carbonate. We need to make a 75 ml solution with about a 5% weight to volume aqueous sodium carbonate solution. So we can do it either proportionally. So if 5% of 100, so if a 5% solution, if we were to make it 100 mLs, that means 5 grams of our sodium carbonate would need to go into 100 mLs of water to make the solution. So if we're starting with 75, how much do we need? So we just cross multiply and we'll get around 3.75 grams. The other simpler way to do it is to just take 75 mLs and multiply it by 0.05, which is 5%, and it'll tell you we need about 3.75 grams in 75 mLs. Once you make this sodium carbonate, you would take 5 mLs of that benzaldehyde from our stock solution that we know is impure and put it into a separatory funnel, which looks kind of like this. So once we have the benzaldehyde in the separatory funnel, we wash it with 5 mLs of that 10% sodium carbonate solution. And we just mix it gently. We don't want to shake it too crazy, or else we'll create an emulsion that can be difficult to separate. So yeah, we just mix it gently, let the sodium carbonate react with the benzoic acid. And once we're done mixing, we put it back onto the loop and just let the layers settle. So you can kind of see there's a layer up here and a layer down here. So our aqueous layer should be the bottom layer, while our organic layer should be the top layer. So now that we have separated it, we will basically remove this bottom layer by draining it, by kind of twisting this hinge to allow for this bottom layer to escape. And once we've removed all of the bottom layer, we collect the top. We do this one more time where we add the sodium carbonate, we mix it, let it settle, and then remove the aqueous layer. So once we've removed the aqueous layer, and we should have pretty much removed all of the benzoic acid. However, there is a chance that we still have water that we, like just H2O, in our organic layer. So to remove this excess water, we dry it using magnesium sulfate. Let's see. So magnesium sulfate, what it'll end up doing is it'll form a complex with the water molecules where it'll form six kind of like this, where it'll react with six water molecules binding to the oxygen to make this kind of complex and SO4 as a byproduct. So this removes all of the water from our organic benzaldehyde. And once we've dried it, we just filter it through a filter paper and collect our benzaldehyde. So once we filter our benzaldehyde, we now have a very pure benzaldehyde that can still react with air and form benzoic acid. So to kind of protect our sample, we use what are known as we use these small crystals of hydroquinone. We just drop them in our, I guess, a beaker and cover it with parafilm, because hydroquinone reacts to oxygen faster than benzaldehyde does. So it undergoes the exact type of reaction, so we have two hydroquinones that can undergo oxidation, where the alcohols become carbonyls. So because this reaction is faster, we end up removing most of the oxygen that's in the beaker, so our our benzaldehyde should be safe. So if we were to run this experiment, what we would need to know is that the magnesium sulfate would go into the solid waste. All of the aqueous waste that we collected from the separatory funnel would go to the aqueous waste, and then we would just clean the hood and we'd be done with the lab. So if you need any more, I guess, guidance on how this experiment could be run or would be run, you could definitely check Dr. Salvador's video that should be right under this one, and you can see him perform the entire experiment from start to finish. And these kind of correlate to that 2850 to 3100 range, as you can kind of see. So using these two kind of key features, we can safely determine that what we're working with is benzaldehyde. However, it's always good to perform more tests. So along the IR spectrum, we also run an NMR. So this is the NMR spectrum we should be getting. So remember, for an NMR, we're checking the different types of hydrogens that are on our molecule. So if we look at benzaldehyde right here, there are four different types of hydrogens. So one connected to the aldehyde, the two here that are closest to the aldehyde, the two here that are slightly further away, and then the one here that is the farthest. So remember, because we can kind of cut this molecule in half and have symmetry, that these two hydrogens on these sides are equivalent. So they should give us the same signal. So the major thing we should know is that the hydrogen connected to the aldehyde should be higher should be more downfield, as we can kind of see here. So in the 10 range. So we're kind of looking exactly right here. Meanwhile, hydrogens on a benzene ring should be anywhere between 8 to 6.5. So as you can kind of see here, we're starting at around 8.2 and to 7.5. So these are our hydrogens on the benzene ring. So using these two pieces of information, we can kind of safely determine that we did purify our benzaldehyde.